All right, guys, here's some basic theory and then some quick examples about moment of inertia. And I'm going to do this as a bunch of short videos. I'm sorry I've done kind of a lousy job explaining it, and I tried to gloss over it too fast, and now you clearly have a lot of good questions. So I'm going to back up. We're going to do a really good job with this, and then we'll be ready to move forward. So hopefully these are helpful and also interesting. So moment of inertia, first thing I want to address is why do we even have this idea of moment of inertia? I think the derivation in the book is a little overly theoretical, and there's kind of a simpler way that I understand it in my brain that I think it might help you get a better intuitive sense of it too. So let's imagine that I have a massless rod rotating about 0.0, and there's a little mass m, a distance r, rotating that way with a velocity v. We also know that if it's rotating, it has an angular velocity omega. Let me focus that. Little angular velocity omega. And I know that v equals r omega from our rotational kinematics. All right, I'm going to write the kinetic energy of this object as 1/2 mv squared. And I can also write that as 1/2 m times r omega squared instead of v squared, because v equals r omega, we know. And then what I'm going to do for no reason at all is do this. It's kind of the part that's spatially dependent and the part that's not spatially dependent. And this mr squared business is what we call the moment of inertia. And it seems kind of silly because I don't really need it to calculate the kinetic energy. I know how to do 1/2 mv squared. That's pretty straightforward. But we'll see when this becomes useful is where you have more than one mass, and you want to talk about the fact that there's something conceptually interesting, which is that when you have more than one mass, they're all rotating at different velocities because they all have different radii from the center, but they all share the same omega. So there's something attractive about representing the kinetic energy in terms of omega and having this other term that's more of a indication of what the mass distribution of the object is. So now let's see how it becomes more useful. Let's say I have the same situation, a massless rod rotating about 0.0, and I have a little m1 here at a distance r1, and then I have an m2 that's at a distance r2, and r2 is the whole length of this. Even I'm just not going to draw a lot on my diagram right now. I'm going to write the kinetic energy again as 1/2 m1 v1 squared plus 1/2 m2 v2 squared, and I can rewrite that as 1/2 m1 r1 omega squared plus 1/2 m2 r2 omega squared. And you can see why this is going to become attractive. Both of these have the half, both share the same omega, and then there's this business that's different. So I'm going to write this as 1/2 times m1 r1 squared plus m2 r2 squared times omega squared. And again, you see I get this mr squared term, one for each mass, and it's the sum of both of them. And what's interesting is, again, this is really telling us, where does the mass live? How is that mass living in this object as they both rotate with the same angular velocity of omega? And that is a better indication of how this moment of inertia could be useful. Now let's generalize it even more and say I have my 0.0, and let's say I have a sort of, some number n little masses, all at their own little radii, all along that point. They're all rotating in their own little circles, their own little, velocities, but they all share the same omega. Well, I can generalize my kinetic energy here as 1/2 based on what I have up here, the sum of I equals 1 to n, where I'm going to do it all along the rod until I get to the end, of mi ri squared times omega squared. And now you can see why it's really useful. For a lot of masses, they all rotate the same, but they have different radii and different velocities, but I could still represent the kinetic energy in terms of some term that really does describe the inertial resistance to rotation. It's behaving in the same way that mass behaves in 1/2 mv squared, but now we're including information about where that mass is as well. And so the definition of moment of inertia for discrete mass particles is the sum of I equals 1 to n mi ri squared. So if you just have like a rod with two things on the end, you can ignore the mass of the rod. You have just two things of mass, and you know how far apart they are from the axis you're rotating. You just do the mr squared. And the cool thing about it being r squared is it doesn't, because it's also v squared, it doesn't depend on whether it's positive or negative. So if I had been looking at this around an axis over there, I would still have, the m's and the r's. I wouldn't go as far either way. But I'd have, it doesn't matter whether r is positive or negative. R squared is always going to be a positive quantity. Okay, so that's cool. I've got my moment of inertia. I can do it relative to any axis that I slap down. We'll see more on that later. What if I don't have discrete masses, though? What if instead I had a little rod? I could think of that rod as a bunch of tiny little discrete masses, dm, each, this is 0.0, each at a distance r. Here's my dm that I've colored in here. And I want to add them all up. I want to do r squared dm, r squared dm, r squared dm, and add it up for all the dm's along the rod. But I can't really do that with an infinitely small thing. They're not discrete. That's where this has to turn into an integral. It's the same idea. I'm doing r squared times m and adding them all up, but now my m's are attached and touching and continuous along this rod. And I'm looking at an infinitely small and infinitesimal dm and adding them up. And so this becomes a more general formula. Instead of a sum, we have an integral. And the limits of the integration are set once you slap down an axis and write dm in terms of spatial coordinates and things like linear density. We'll see how to do that. But once you, so you'll be able to set the limits here, just like we have I equals 1 to n. Think of it as like integrate over all the little masses of r squared times dm. And the goal of this is always to write dm or an r in terms of some variable so that we can perform this integral. This integral doesn't really make any sense right now, but conceptually we're taking all those dm's and their associated r's and we're adding them all up. And so these are the two ways that you calculate the moment of inertia for discrete masses and then for a continuous body. And we're going to take this and calculate some stuff in a second.